there is source code for this talk. It's at that URL. Currently this is APGL source code, so it just shows you what we do. We're hoping we can get it to MIT license very soon, so you can actually use it. Okay, I'm going to try to structure the talk like this. There are two main points to this talk. One is why you would ever write a full-text search engine in Go. It wasn't something I expected to ever do. And the second is how you do it. And it wasn't obvious to me that it was possible before I started it. Okay, anyway, we'll see how close we stick to the schedule. This is me. The important thing here is that I work in document processing, and what I hope to show today is how someone who understands their domain and is not a particular expert in Go can write useful production software pretty fast. I work at a company called PaperCut. PaperCut makes print monitoring and printing software. This software is pretty much classic system software. It runs close to the hardware, it's tightly coupled to the operating system, and it needs to perform quite well. And in our case, we need to run on a variety of operating systems in the cloud, and lately we run on edge nodes. This is particularly important for printing software because people need to be able to print even when they're not connected to the internet. So the software we write typically runs on a computer inside a customer's premises and connects to the internet when it can. PaperCut's been using Go for a few years now. Firstly, for the reasons, firstly because of the characteristics of our software in the previous slide, but secondly because it's a very practical language for writing system software, and I'm sure a lot of other speakers will talk about that. The particular part of the PaperCut software I'm talking about today is something called an IPP print server. This is a print server's a bit of software where it takes in jobs when you push the print button in your application and sends it off to a printer. It's currently PaperCut's second biggest product, and I think we've got about 10 million end users at the moment, but it's relatively new, and we hope to grow that quite fast. Okay. This particular protocol, IPP, is HTTP based. It's used all over the place on all Macs and Linux systems. It's also used for most mobile printing through AirPrint. The important characteristic of it for the purpose of this talk is that internally it uses PDF for its document format. Interestingly, for a Go conference, we wrote our IPP server in pure Go, and we just built it on top of net HTTP, and it works really well. So that was nice for us. And as I was saying, the last point here, it's basically just standard Go libraries plus a whole bunch of work from us. Okay, now that we've got all these IPP servers with lots of customers, the next step we want to do is to see if we can add some value to them. One of the ways we can add value is to allow users to search the documents that we're holding before we print them. And here I've listed three classes of users. The first one is what we call a print alert. That's where we have a fixed search and then we apply it to jobs as they come in. and we perform actions based on matches. So if we want to say, so if a customer wants to prevent a particular class of document, they can just delete the job, or they can pop a dialog box or do something like that. Second class of applications is being able to search over the user's documents. An example here would be in say a travel shop where the documents might be various types of brochures. Here, someone in the shop could search the particular brochure they want and print it. The third class of application is one that we just tried out recently. And the idea here is that we add a QR code to documents. Then when people scan that QR code with their phone, they get linked to the digital documents, and they can start to do some kinds of online actions on their paper document. And the particular one with search is to be able to search their document and find the page they want. And the classic case here would be if someone's got a manual of, say, 500 pages, which is hard to search on the physical paper, by scanning the QR code and doing a search there, they can be directed to the appropriate page. Okay. So now we have to write this full-text search over PDFs. So the obvious answer here is just to use an existing program that does this, and there are some that do it very well, the main one being Elasticsearch. However, our product developers gave me an extra set of requirements. Remember that they want to run on edge nodes, so they want to. That means they need to run on they need to run on a variety of OSs. But in particular, they need to have a small memory footprint because they need to be able to bring up these nodes fast. So this ruled out the obvious libraries because they're all Java-based, and our product developers don't want to run JVM. So given that, our option then is to, at this stage, I looked around to see if there were any other libraries that worked in, say, pure C or Go. There weren't, and we were then forced to write this ourselves. Not only that, our product developers threw in an extra requirement. They wanted to be able to. They wanted to get the results back in an easy-to-read form. So I've shown this here with some pictures. In this case, someone searched for the term cubic Bezier curve, and they want the results highlighted like this so they can show this to their users. And by the way, you can see here that this actually is a full-text search because it finds all the different capitalizations and plural forms of words. Okay. So you might wonder why our product developers want that. So that requires understanding a little bit about the PaperCut products. One of the ways that PaperCut adds value to printing is that instead of users printing their documents, all the documents go to a printer, then users walking up and having to search through the pile of documents on the printer. With PaperCut, you print you print into PaperCut. PaperCut holds the jobs. Then you can take your phone up to a printer and identify yourself either by scanning a QR code. Identify the printer by scanning a QR code or finding a near field beacon, and then on your phone. Print your job on that printer. That works really nicely. And to make it even nicer, we can see up here that when users are selecting their jobs at the printer, they get a preview just to check that it's the right job. So that was the basis of this requirement. so that users can see their jobs, they can search for particular terms, and then that will be highlighted nicely here in the preview. Okay, so given all these requirements, we then have to figure out how to write a full text search in Go. So, writing a full PDF, a PDF full text search pretty much always falls down to these 5 steps. First, we have to extract the text from the PDF. Then we do the full text search on the extracted text, not on the PDF. So the mistake there. And a full text search engine will return the best matches. So this is a full text search engine is like a Google search where you type in a term, not necessarily exact text, and you get back the closest matches. The next step is to find the PDF documents that match the page numbers and the locations of the matched text on the PDF pages. In our case, we want to mark up the PDF pages with the location of the text as I just showed. And if we're shipping this out, these marked up pages out to clients, we may choose to send them thumbnails, rasterized thumbnails, rather than a full PDF if the client doesn't have a PDF viewer. Okay, now in order to do this, we need the following bits and pieces. We need a library that will extract the text from a PDF. We need a full text search library that will search the extracted text. We need another library to mark up the PDF with the matches, and then code to integrate all this and get it working. So at this stage we have to choose libraries. Now, Go's been working pretty well for us for a few years, so our first attempt was to see if we could find Go libraries to do this. The first library we needed was the text extractor. We could find no libraries that did this, but we had a library that was working pretty well, which was this Unidoc. So I wrote a text extractor for Unidoc, made a pull request, and got it integrated. Now that's a fair bit of work, and I don't want to gloss over it too fast, but the point is that if you're a PDF expert like I am, it's not that hard. And the nice thing was that it wasn't that much extra work to do it in Go. And this speaks a little bit to the maturity of the Go ecosystem at the moment, that in addition to getting the libraries that do the things you need, in cases where the libraries don't do what you need, going and extending them is possible in a lot of cases. And that's a very nice thing for companies like us, where we do things that aren't always in standard libraries. Okay, the second component here is a full text search engine. A quick look around found a library called Bleve, which seems to work really well. For those of you who are familiar with full text search, the most well-known library is Lucene, which is a mature Java library. Bleve is much newer, much simpler than Lucene. But the key point here is that it has all the features we need, and we really don't need that many features. So what we get to do is we get to satisfy all our developers' requirements, which are a relatively modest set of features, but a small memory footprint, and in particular to avoid the JVM. So Lucene's a great library, but Bleve actually works better for us. Okay, so they're the two libraries. Now we actually have to go and write the full text search engine. And here to do it, there's one key bit of knowledge that makes all this easy. For those of you who don't know PDF internals, which are probably the majority of you, this is it. The key bit of knowledge is that PDF is a general purpose graphics language. It's not a text markup language like HTML. And that means that there are commands for drawing any particular any kind of graphic objects on a page in PDF, and text is just one of those. In this case, I've shown how to draw a hello world at the top of an A4 page. The key thing about this is that the text doesn't appear sequentially in the PDF file. So in order to be able to convert a PDF file to text, you have to be able to find the location of the text on the page. Okay, well, once we know that, we then know how to write a full text PDF search engine, which I'll explain in the next few slides. And the key idea here is that we can use the positions of the text on the position information of the text to go and do everything we need to do. Okay, so these are just some structs and function prototypes out of the code, and the idea is really very simple. So we just write a Go struct to represent the text and its location. So the text is a string, the location is represented by a box that encloses it. And in the previous hello world example, would be a text mark for the hello and a text mark for the world. It's just it's based on how the text is represented internally in the PDF. Okay, and so the way we write the program is this. We take all the text marks, then we figure out, use location information to figure out the extracted PDF text. That algorithm is conceptually straightforward. We sort the text by its height, then we set the text by its Y position, then by its X position. When we go through and looks for gaps in the Y position, so as the text goes down the page, and if we find the Y position dropping enough, we assume it's a new line. That gives us the lines. Then in each line we go through, go from left to right, and if we find a big enough gap between characters, we assume there's a space. It's more complicated than that, but that's the basic idea. That covers text laid out as lines on the page. Columns are more complicated, subscripts and superscripts are more complicated, as are tables, but they all work basically the same way, and we can do this. Okay. At the end of that, we end up with a slice of the text marks. So we end up with extracted text. But what we then do is we sort our text marks that we use to generate the extracted text. We just sort them by their offsets in the extracted text. The reason we do this is that any process we're going to do on the extracted text will give us some kind of substring, which is and a substring is two offsets in text. It's the start and the end. Okay. So anyway, so given this, we go off, search the extracted text. Once we have the extracted text, we can then search the text marks. This is the array that contains the location of the text on the PDF page. But we search it by the offset in the extracted PDF text. Once we've done that, we've got a bunch of text marks, hello world, which represent the substring in the extracted text, and to find the rectangle around those, we just take the union of the rectangles, and that's it. So that may have seemed a little bit complicated, but it's really not much code. It's a very simple idea, and it's all just based on a little bit of so it's just based on that one understanding of how PDF works. The function look like this. There's a array of the marks on the page. There's a function to extract them, all kind of obvious. So this is how the program works. There's in order to find the text marks within a range of offset in the extracted text. So we take the extracted text, long, say big long text, we search for some search term which is it's a substring in the big text that has a start offset and an end offset. We put them into this function, and that returns the text marks corresponding to that substring. We have another function that gives us the rectangle that surrounds all the text marks, but as you remember, it's just the union of the rectangles of each text mark. So these are, I'm showing function prototypes here, but there's almost no code. It's a very simple idea. Okay. The next step is to interact with the full text search engine, and Bleve is really, really simple, which was nice. Bleve indexes over, you feed Bleve a struct, but internally Bleve has an ID which will tell you you feed Bleve documents. In our cases, the documents correspond to pages of PDF text. This would be the extracted text. And you also feed Bleve an ID that identifies that particular document. You run it into Bleve. Bleve creates an index over all the documents, and it does it quite efficiently. Okay. Next step is to perform a search over the Bleve index, and Bleve performs these powerful full-text searches. It looks just like this, gives us back something called a search results. Okay, and inside a search result is some information, and the key bit we need is the start and end of the positions of the matched text, the result of our query, in the extracted text. Looks like this. We feed that back into the previous functions, find the bounding box, and mark it up. And we get a result that looks like this. In this case, we've searched for insect biomass. And that's how it all works. I think I'm well ahead of time now. Okay. So it really was that easy, which was nice for us. What I've left out here is, I've left out an additional complication. While this was all very compact, we got a further request where people wanted, instead of having to write a Bleve index to disk, they wanted all serialized into a byte slice made very compact so that they could run their web app and create an index, push the index over the web, get it back, all super compact. That led to the code I've just written there to double in size. But again, it was just another straightforward step where we found a serialization library, figured out how to make our structures more compact, zipped up data again. Okay. So that was it.